Comparing linear, quadratic, and exponential functions. So first we're going to start by comparing them and determining what type of function they are by looking at their graph. So here's a couple notes for you. It says linear functions form a straight line. Quadratic functions are U-shaped. Remember, we call this a parabola. And exponential functions have these curves. They're either increasing, what we call growth, or decreasing, which we call decay. So with A, it's a straight line. So this is a linear function. So that one's linear. B is in the shape of parabola. So this is quadratic. It's in the shape of that U. And C has that nice little curve, which we should recognize as exponential. More specifically, exponential growth, but it just says linear, quadratic, exponential. So that's how you tell. So linear, straight line, quadratic in the shape of a U, which we call a parabola, and exponential has that sort of curve. So you do D through F. So now let's determine by written descriptions. So here's some notes for you. I'm not gonna read those for you. You can go ahead and read those yourselves. But so for like number two, it says determine whether the following situations would be best modeled by a linear, quadratic, or exponential function. So when I kind of read these descriptions, I often like to just think of it like visually, if I were to graph it. So A says the height of a water balloon after it's launched up into the air. So if you thought about it graphically, and you don't need to draw this, but if I put it on a graph, after I launch a water balloon up, it's going to come back down. It's going to form a U shape, right? U shape. So that's going to be a parabola, which would mean that the answer to this one, this is quadratic. That would be for A. B says total money earned while working a job that pays $12 per hour. So you're just getting $12 per hour. So $12, $24, $36, $48, $60, $72, $84, just going up by 12s each time, correct? So that would be a linear increase, right? I mean, look at it, it's 12, 24. It's going up by the same constant amount each time. If we were to graph it, it would be, after 1, it'd be at 12, then it would be at 24, then it'd be at 36. It's just going to be after, it's going to be a linear relationship. So this second one, I'm going to say is linear. C says your credit card has an annual interest rate of 16%. So really only dealt with interest, or sorry, percentages with the exponential unit. This is going to be exponential. Because if your percentage increasing, then it's going to grow by a exponential rate. Because if you do 16% increase, you're going to go 16%, and then you're going to do a 16% off of that, which is a greater sum, and then another 16%. So this is going to be exponential. But if you to do a function for it, remember we put 1.16 to the power of x. Anything with percentage rate is always going to be exponential. So you try to do D, E, and F. Oh, and 3, 4, and 5. Try to create your own. Okay, tables. Okay, so this might be what I think sometimes a little bit harder than the other one. So here it says linear functions have a common first difference. Quadratic functions have a common second difference. And exponential functions have a constant percent rate of change or a pattern of multiplication division. So 6 says determine whether the tables represent linear, quadratic, or exponential relationships. So A, if I'm looking at this relationship here, specifically in the y values, if I try to see what pattern's happening here, it definitely doesn't look like it's first difference, like it's adding the same amount each time, right? It goes 8 to 16 to 32 to 64. This definitely looks like a multiplication, a timesing by 2. And since it's multiplying, this is exponential. So that represents an exponential relationship because of the multiplication. Remember, that's what it means to be exponential. Now, B, this certainly doesn't look like any multiplication going on, but it does look like it's adding the same amount each time. Looks like it's adding 7. right? So that's linear. It's going up by a constant amount each time. Now looking at C, it certainly doesn't seem exponential to me. 5 times what is 8? I don't know. It's if I do 8 divided by 5, it's 1.6, but 1.6 times 8 is not 15. It's definitely not going by a multiplication pattern, so it's not exponential. In terms of its pattern here, this goes up 3, and then it goes up 7. So it's definitely not linear either. But this is quadratic. And let me show you how we can tell. If you looked at the notes above, for it to be quadratic, that means its second difference needs to be the same. So let me show you what I mean by that. So this 15 and 26, that's plus 9. And that is plus, no, that's not plus 9, that's plus 11. Sorry. And that's plus 15. So the first difference is the same. It goes plus 3, plus 7, plus 11, plus 15. But the second difference is, look, plus 4, plus 4, plus 4. That's how you can determine whether or not a table is quadratic, is if its second difference is the same. Now, some tables it might be easier to tell that's quadratic just by looking at it, right? If it kind of forms a U, if it goes down and then back up with the Y values. But sometimes you're not going to see that within the table because of it might not show you a particular X values that are going to show those Y values go down and back up. So really, the surefire way is to look at the second difference if you're trying to figure out if something is quadratic or not. Okay. So yeah, I'll let you finish it.